Hello, welcome to Maths with EJD. In this video, we're talking about multiple regression analysis. In the previous video, I had talked about simple linear regression and regression. Multiple regression actually it extends simple linear regression. It extends simple linear regression by modeling the relationship between one dependent variable and multiple independent variables. So you remember that in the case of simple linear regression, it is one dependent variable and one independent variable. So, but in the case of multiple linear regression, we have one dependent variable and multiple independent variables. So this then allowing us to evaluate the combined impact, the combined impact of predictors on the outcome. Okay, so definitely so you can see from here that the independent variables, the independent variables the independent variables are also known as predictors. Independent variables are predictors. The same idea applies in data science or what you can call machine learning. Then the dependent variable can be seen as the target. Dependent variable would be the target. So the predictors can be used in predicting the values of the targets. Okay, so let's go on to um the definition itself, the mathematical definition. As the first step here, definition of multiple regression. Okay, so multiple regression models the relationship between a dependent variable y and several independent variables, several independent variables like x1, x2, x3 up to xp. These are the predictors. So, and it uses this general formula using the following general formula. That is y equals beta naught plus beta 1 x1 plus beta 2 x2, beta 3 x3, and all of that up to beta p xp plus the error term as usual. So where y is the dependent variable, y is the dependent variable, or what you can call the target, if you like, call that a target. Then you have x1, x2, x3 down to xp. These are the independent variables. Independent variables. or you can call them the predictors. So the predictors. So then, of course, you have the beta naught. Beta naught is the intercept. And just like we learned with simple linear regression, the intercept is like the base value that is, if nothing else is working, if there is no x1, if x1, x2, x3, and all of the x's are zero, then you have b naught. Like, that's like the minimum you can ever have, like that. So that is your b naught. That's the intercept. Then you have the I mean beta, right? Beta naught. So you have beta one, beta two, beta three, then all of that up to beta p. These are actually regression coefficients. So just like we learned with simple linear regression, right? This this beta values actually amplify any units in any units of x1, x2, any unit of x1 is amplified by beta 1. Any unit of one, okay, let me put it this way. One unit of x1, adds beta 1 to the value of y. One unit of x2 adds beta 2 to the so whatever value of y based on every other determinant, right? And so on and so forth. That's the kind of thing. So you have this as the the regression coefficients, like that. And lastly, you have the error term as usual, because once you have this kind of thing, the error is uh, you might have error in the situation. So epsilon is the error term, and that is more like what you can see as the unexplained variance in the results. Unexplained variance. Unexplained variance. Okay. So um imagine, let me just do a kind of example. Okay. So you have an example like this. You want to, yeah, suppose, let me put it this way. Suppose you have the objective to model salary salary y as a function of experience, which you can call X1, and education. So you want to see how much salary someone gets based on their experience and their education, which you can call X2. Okay. In this case now, you see the you see that salary of course is the target. Salary is the target. Then experience and education are the predictors of salary, right? So that's why they are predictors of salary. Of course, the target, as you know, is the dependent variable. So it means the salary depends on experience and education. So dependent variable, and these are actually the independent variables. Independent variables, like that. Okay, so if you have that kind of situation, how do we go about handling that? So let's go to step 2 now. We have the problem and data of this example. We have talked about problem and data. Okay. Um, so once you know the problem you want to solve, the next thing is you want to get the data that is relevant to the problem. So we aim to predict, an employee's salary, an employee's salary using the following data set of 10 employees. So you want to get the information of 10 employees, including their salary, experience, and education, to see how you can model, how you'll be able to predict anybody's salary, any employee's salary based on the experience and education. So here now we have 10 employees, like we said already. So you have the employee, you have the salary, you have the salary, which is Y. You have the experience, you have the experience, maybe work experience or things like that, X1. And then you have the education, you have the education, which is X2. Education, that is X2. So So let's say that the first employee, the salary is 55. Let's say in hundreds, right? Let's say the salary is $55,500, or let's say $5,500. And then we have the experience. The person has 5 years experience. The education, maybe the number of years spent on education is 16, depending on what level of education they've acquired. Then you have two, salary of 60, the person has experience of 7, and then education, studied for 15 years. Then you have 3, employee 3, $7,200 salary, 10 years experience, and 18 years of studying. Then you have employee 4, 5414, employee 5, employee 5, you have 65, 817. Employee 6, you have 80, 12, 19, 80, 12, 19. Employee 7, you have 58, 6, 16. Then you have employee 8, employee 8 and $6,700, let's say per month or whatever we choose. Then 9 years of studying, 9 years of experience, 18 years of studying, employee 9, and then employee 10. So employee 10, employee 9 earns $4,500, 3 years of experience, 14 years of studying. Employee 10 earns $7,700, 11 years of experience, and 19 years of studying. So this is the table we have. This is the table we have now. Okay, this is the table. Okay, now let's go on to see what we can do with that. So our job is to predict. We will predict employee salary, employee salary based on experience, based on experience and education using multiple regression. That's our task. So that takes us to point 3, where we actually talk about multiple regression model. So we have multiple regression model. Okay. So the specific model used is salary equals beta naught plus beta 1 multiplied by experience, plus beta 2 multiplied by education, plus the error term, like that. So that's the general form of that. So of course we know salary is a dependent variable, experience X1, education X2 are the independent variables. B naught is the intercept, so I can refer to those. B naught now is the baseline salary. Baseline, this is like the baseline salary. So even if you have 0 experience and zero education, you earn beta naught. That's what you can consider as some kind of minimum wage. Even if you have nothing, if you have not got any education or you have no experience, just come like that. You have to earn at least beta naught. That's the minimum wage kind of thing. So baseline salary when predictors are zero. When predictors are zero. Again, that's like minimum wage. So, of course, beta one, beta two, like we said before, they are regression coefficients. Regression coefficients. Cause this is predictor one, predictor two, meaning they are the independent, I mean, the independent variables one and two, like that. So that's the multiple regression model we need. So the next thing we want to go to is to do the model fitting for model fitting. So we want to fit the model to the data we have. Model fitting. So here we want to use ordinary least squares, ordinary least squares, which is also known as OLS, to fit the data, to fit the data. So here, because we have to fit the data, right? Because we have multiple stuff here, it's not as straightforward as what we got the other time. So here we need to actually put we need to do some kind of matrix thing. So let me pull that off right now. That's how we go for this. Um, just a minute. Yeah, good. So here you can see that we have the X values, right? This is the general way to go. So using ordinary least squares to fit the data, right? To fit the data, um, the coefficients, the coefficients are estimated, are estimated. Okay, or let me put it this way. Using ordinary least squares method to fit the data, or let me put it this way. I want it to sound to come across better. Okay. So let's talk about model fitting again. Yeah, let's go this way. The coefficients are estimated using ordinary least squares. That is OLS, which minimizes the sum of squared residuals, the sum of squared residuals. So the matrix form of ordinary least squares is given by beta cap equals X transpose X inverse multiplied by X transpose Y. So that's how we get the B's. So of course, this X you have now, they are actually matrices. So here, where X, any X you see there, is actually the design matrix. It is the design matrix. So X is the design matrix. And that includes including the intercept, and the independent variables. Okay, then we have y. Y is the response vector, which is actually the vector of the target. Okay, the vector of the target, or better still, since we talked about independent variables there, so that would just be the vector of the dependent variable. Okay, so for our data, the matrix X, now it has to include, because we have two independent variables, x1 and x2, but then the coefficient, the intercept too, is there, so we have to represent that with something, right? Because that's beta naught, it doesn't have any x attached to it. So to make up for that, we have, for our data, the matrix X, which is now, we now include column of ones for the intercept, you know, columns of ones for the intercept. Of course, one multiplied by anything will just give us that thing back. And then vector y and vector y. So if you look at the information again, 1, 5, 16, 1, 7, 15. Okay, 7. So we have all this 55, 60 and everything. So 5, 16, 7, 15, 10, 18, 4, 14, and so on and so forth. That's what we're going to be having down there. So here, X will now be, so 10 of them, right? So you have 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. Okay. That's for X. So then we have all, so that's for the beta knots. So you have 5, 16, experience and education. 5, 16, 7, 15, 10, 18, 4, 14, 8, 17, 8, 17, 12, 19, 6, 16, 9, 18, 3, 14, and lastly 11, 19. So this is our response vector, that which contains, so this is for beta naught, this one represents beta naught, then this one represents for the variables, right? So this is like for the beta, the coefficient of beta ones and the coefficient of beta 2, or I mean the variables in short. So this first one corresponds to beta naught, this beta 1, this beta 2, like that. And of course, we have y, which is what is called the response vector for the dependent variable, or what you can call the target. So this will be, all the salaries we have in the data. That's 55, 60, 72, 50, 65, 80, 58, 67, 45, you know, like that. So that's what we're going to have here. So we have 55, 60, 72, 50, 65, 80, 58, 67, 45, and 77. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is our response vector. And don't forget, the whole beta is going to be X transpose. So it means the transpose of this X multiplied by X itself. And all of that will now be multiplied by then we find the inverse of that, and then X transpose Y. So that's a lot. If you want to try this out, I don't think I want to try this out right now. Or maybe I'll just write that matrix out based on this thing and just leave it there and go. So let me just do that. At least let me try to do that. But that's gonna be a lot. I'm wondering. Okay, well, once you have these two matrices, right, just go you need X transpose, this is, so we need X transpose. X transpose will just be, this is actually a 10 by 1 matrix. X, it's a 10 by 1 matrix. So X transpose is going to be 1, 10 by 3, sorry. 10 rows, 3 columns. So the transpose will be 3 by 10. That means you're just going to have, uh, you know, we're going to have 3 by 10. That will be 1. So on one row, you're going to have 1, 1, 1, 1 like that. And then you have 5, 7, 7, 5, 7, 10. So it will be like something like this. 1, 1, 1, 1, 1, 1, 1 in template. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the other one is going to be, so you're going to have 5, 7, 10, and so on and so forth. Something like that. So it's, and then the last one is going to be 16, 16, 15, 18, right? On that row, 16, 15, 18, and so on and so forth. So yeah, this is your X transpose now. Okay, that's X transpose. And then what else do we need? We need X. Of course, we already have X itself. So we're going to multiply this. So we're going to have X transpose X. So this X will be multiplied by this X transpose. Then whatever you get to find its inverse. Inverse is not that easy to get. But of course, you can refer to my matrix playlist. Then you now have X transpose, again, this X transpose multiplied by Y. So this is going to give you the beta cap, which contains the intercepts and the independent variables. So, but I mean, I'll just go straight to the answer. Then I'll make another video I'll write a Python code which makes everything simple, easier to implement. All right. So we have, okay, I think what we have been doing so far here is the matrix representation. Then the next thing is to talk about the estimation. So if you do all this computation, right? If you do all this computation, we can say we compute, so we compute the coefficient, we compute the coefficients using ordinary least square, I stated already, which which provides the following fitted model, the following fitted model. So if you go through all this process, you get this following fitted model, which is the salary. Okay, I guess I want to do that in red or this color. Salary, based on the model, if you do all that, it's going to be 26.64. This is beta naught, right? Plus 3.37, 3.37 multiplied by experience. Okay, then plus 0.66 multiplied by education. That's what you get. Okay. So if you do that properly, that's what you get. So now this is beta naught, this is beta 1, and this is beta 2. So that's what you get if you do that correctly. But because it's a matrix thing, if you want to embark on that, it can take the next 1 hour, in fact. So let's just, but of course, if you have time, you may want to really try your hands on it. And if you don't know how to go about it, you can actually you can check my playlist on matrices, so and see how to do matrix multiplication. It will be well explained right there. So let's go on to talk about the meaning of the intercepts. Uh, I mean, interpreting the coefficients, right? So we say interpreting the coefficients that we have obtained now. So first we have the intercept, the intercept, which is beta naught, and that is equal to 26.64, 26.64. What does it mean? So this is the predicted salary. This is the predicted salary for an employee, for an employee with zero experience, with zero experience and education. So this is like the baseline salary. If you don't have any experience or education, you're going to earn 26,640. That's 26,000, 2,664, whether dollars or whatever currency you're thinking about. So, of course, this may be unrealistic, right? While unrealistic, it serves it serves as a mathematical baseline model, as a mathematical baseline for the model. Okay. So it may be unrealistic, but that's what the maths is giving. So the next part is the experience part, which is beta 1. Experience, that is beta 1 equals 3.37. So what it simply means is that for each additional year, for each additional year of experience, the salary, the salary increases by, it is in hundreds, right? The salary will increase by $3,370. So if you multiply this by 100 now, uh, okay, I mean, if it is in the thousands, I think it's in the thousands. If it is in hundreds, you just multiply by 100, right? But since I've been talking about 100, let me just maintain the same energy. Okay, let me just maintain the same energy. Yeah, let me just maintain the same energy since I've been talking about hundreds. So for each additional year of experience, the salary increases by $337, so to speak. So, and in that case now, holding education constant, that's if you don't tamper with education, holding education constant. Okay, then we can talk about the education itself now. We can talk about education, which is beta 2, and that is 0.66 from the model. We get 0.66. So as beta 2 is 0.66. So in this case now, for each additional year of education, for each additional year of education, the salary increases. The salary increases by multiply by that. If you're talking about hundreds, or okay, let me put it on record. Let's talk about thousands. It makes more sense, right? If it is in thousands. So let's do it that way. So for experience now, for each additional year of experience, the salary increases by $3,370, while for education beta 2, which is 0.6, is for each additional year of education, the salary increases by $660 when you multiply that by 1,000. So in that case, we are holding experience constant, holding experience constant. Okay. So but you can see that this effect, you can see education counts less in this case. This effect is smaller. This effect is smaller and less significant and less significant than the effect of experience. Okay. So, of course, this is the reality in many situations. Like the longer you stay studying, the less your capacity to earn big, But so you have to choose your choice carefully. So that's one thing that really happens. Okay. Um, so we can actually do some kind of model evaluation. Let me see. I want to really make that as clear as possible. Hmm, okay. Yeah, I want to include formulas and everything, so I'm careful to be sure I have everything in place. Let's see. So now we're talking about model evaluation. So there's some information you can actually draw from the model. Yeah, let's go this way for model evaluation. Um, Model. This is like step 6 now. What we have done so far. Well, okay, that was step 4. That was step 4. Yeah. So this will be our step 5 now. Step 5. That's model evaluation. So now you've got the model. How do you evaluate it to see some things that are really important? So the first evaluation we'll talk about is R squared, which is called the coefficient of determination. How do you evaluate your model to see if it is performing well? So you have the coefficient of determination. In this case, um, say that R squares measures the proportion, measures the proportion of variance in the dependent variable, the dependent variable, which is salary in this case, the salary in this case. So the variance in the dependent variable explained, which is explained by the independent variables, by the independent variables. It is calculated, it is calculated as R squared equals 1 minus SS res over SS total, SS tot, where where SS res is equal to sum of squared sum of squared residuals, sum of squared residuals, which you can call unexplained variance, okay, divided by total sum SS dot, which is total sum of squares, total sum of squares. In this case, that is total variance in salary, total variance. So unexplained variance in salary is SS res, and total variance in salary is SS dot. Now, what this actually means is that when you predict the salary, right, there are variants that can be explained by the actual independent variables you have, and there are some variances you cannot explain by the independent variables. So in that case, but the total variance is now unexplained variance plus total variance is unexplained variance plus variance explained by the independent variables. So for our model now, without going through all the stress, so for our model, for our model, so when things are becoming this complicated, it's better to use coding to resolve the problem. So for our model, so if you compute for a model, as you're going to see when I write the code, so for R squared is 0.994. So what this means is that, so R squared is 0.994, meaning that 99.4% of of the variance in salary, of the variance in salary is explained, is explained by the model, by the model, indicating an excellent fit. So if the model can explain 99%, if the variance of meaning that the 95%, if 99.4% of the variance can be explained by the model, then that means that the model is an excellent one, indicating an excellent fit. An excellent fit. Okay. Now, um, the next the next evaluation we can do for a multiple regression line is B. B now would be adjusted R squared. So adjusted R squared seems to do a better job than R squared, like to remove some kind of ambiguity. So let's say uh adjusted R squares, adjusted R squares actually adjusts its adjusted R squares adjusts for the number of predictors. So adjust for the number of predictors, preventing overfitting. So if you want to prevent overfitting, overfitting is something that we get to deal with. We deal with a lot in machine learning. So adjusted R squared adjusts for the number of predictors, preventing overfitting. It is calculated. It is calculated as adjusted R squared, which is equal to 1 minus 1 minus R squared here into n minus 1 divided by n minus p minus 1. Okay, the classic me, I shouldn't have done it this way, but it's okay. So here now, uh, n n is number of observations. Number of observations. For the data we have, that will be 10. Number of observations, that's the education experience pair. So that's 10, like that in this case. Then P, right? P is number of predictors. P is number of predictors, which will be 2 here because we're talking about experience and education. So number of predictors, that is 2 in our case. All right. So of course, you know R squared already. That's the R squared we got previously by saying 1 minus SS rest over SS thoughts, like that. So we have that. Okay, so we go again and say for our model, right? If you put the R squared, you have the N, you have the P, you have, we can say that for our model, um, adjusted R squared, adjusted R squared is equal to 0.993. That's still excellent, 0.993. And this further confirms, so confirming that the model, remains a strong fit, remains a strong fit even when adjusted for the number of predictors. Okay, so that's a nice one. Even when adjusted. Then another thing we can have is this. We have the uh F test for overall model significance. We can have that. That is C F test for overall model significance. So F test for overall model significance. So the F test, assesses whether the model, whether the model as a whole, the whole model now, whether the model as a whole is statistically significant. You can get an answer that is not statistically significant. So you don't have to reckon with that. It's statistically significant. So F statistic, the F statistic is calculated as F equals R squared over P divided by 1 minus R squared, all that divided by N minus P minus 1. Okay. So we come again. F statistic. Okay, I mean, for our model again, I always like to put this in a separate color, but it's okay. I keep forgetting, but it's okay. So now For our model again, for our model, if you put, of course, we know all these things. We know R squared, we know P, that's the number of predictors, and we also know N, that's the number of observations. So if you put all of that, you may want to check this to be very sure if it's correct or not. So for our model again, F F statistic p-value, F statistic p-value is equal to 1.50 times 10 raised power minus 8. And that's really small because usually we want p-value to be less than 0.05, and this is like 0.6 or 70150. That's pretty small. So, and that indicating, right, that the model, the model is highly significant. Model is highly significant in predicting salary. Okay, another thing you can do again is to, apart from this now, you can actually choose to do, we are evaluating the model. So we have seen so far we can actually we can look at how much of the variance in the prediction is explained by the independent variables, how much is unexplained. That's R squared. Then we can adjust for predictors using adjusted R squared. Then we can test for the significance of the whole model by using an F test. Another thing we can do again is to do t-tests. We can actually do t-tests for individual coefficients. So some coefficients may be more significant than the others. So we can do t-tests for individual coefficients. So that way you can explain your model thoroughly, right? So here the t-test checks if if you write a Python code for this, it's going to give you all of these things in one blow, right? So the t-test checks if each coefficient is significantly different from zero. Okay, right? So for instance, if we go talk about experience, you know, experience, the p-value, the p-value for experience, p-value for experience is very small, is very small, and that is p is less than 0.001. Okay, indicating indicating that experience has a significant positive effect on salary. Okay. And then when we talk about education, for education now, you have the p-value for education is 0.264. So this now is big, very big compared to what we had before. So showing it is not, so education is not statistically significant. So showing that it is not statistically significant after controlling for experience. After controlling for experience. Okay. So we have all that. I think with this now, let me see what else we can talk about with this. I think everything is looking done. Let me see what else we can add. What else can we add? Okay, yeah. I mean, these are the key parts now. So, first of all, we have the definition. We have the definition of multiple regression analysis. After the definition, the next thing is we want to take a case study where we predict salary based on education, experience and education. And then the next thing is we try to do the multiple regression model. So if in that case, now we're going to be having, we looked at having salary equals beta naught plus B1 times experience plus beta 2 times experience plus the error term. And then we did the model fitting using ordinary least squares. And this is really significant. This is important, this expression. So if you want to try it manually, this is the formula to use. And I tried explaining that here. So this is what the matrix looks like. This is your Y. And I tried to explain what X transpose means. Like a 10 by 3 matrix becomes a 3 by 10 matrix when you transpose. So you multiply the transpose by the ordinary normal matrix. After that, you find the inverse. That's a tedious process. Then you can also multiply the transpose by Y, and then you multiply it together. You get the result. So if by the time all that is done, then you get this beautiful result. You get this beautiful result that salary is equal to 26.64 plus 3.37 times experience plus 0.66 times education, and then you interpret the coefficient. So 26.64 means that if somebody has no experience and education, at least they will earn 20, multiply that by 1,000, that's 26,640, you know. That's what it means. That's baseline salary. We can see that more like annual salary. Then the person will earn 26,640 annually. Then uh, for every unit of every 1 year of experience, the person earns 3.37 times 1,000. That's $3,370 extra. That's if education is kept constant. And if experience is kept constant, the person earned for every one additional year of education, the person earns $660. That's if you multiply 0.6 by 1,000. If we are talking about those values, like in essence, we are saying that the data we have in the table, this salary is in thousands of dollars. Okay. That's that's the assumption. Okay. That's why we are multiplying by 1,000. So, I mean, if you put the 00, it can give you more trouble. So it's better to put it aside. Just know in one corner of your mind that it is in thousands. Then, okay, I've explained all this. So the next thing is to evaluate the model itself, how well the model performs on the data. So you can do coefficient of determination to explain the variances. So in explaining variances, you can use R squared and adjusted R squared. That's adjusting for the number of predictors. And then you can do a F test for the whole overall significance of the model. Then you can now even go to individual coefficient to see how significant they are. In our case, you see that experience is really significant in predicting salary, whereas education, though it contributes a bit, it's not as significant. It's not really as important as experience in predicting salary. Okay. So with that now we can wrap it all up and say that uh, the multiple regression analysis, the multiple regression analysis shows that experience is a strong predictor, the strong predictor, at least going by the data we have, right? If you use another data, you might get something different. But based on the data we have, that's our conclusion. The multiple regression analysis shows that experience is a strong predictor of salary, while education has a smaller non-significant effect. Okay. Smaller non-significant effect. So the high R squared, that is coefficient of determination, the high R squared value and significant significant F test indicate and the significant F test indicate that the model fits the data well. Again, the positive coefficient. Now, if the coefficients are negative, for instance, if you get like minus 0.66 for education, it means that for every unit of experience you have, your salary is reducing, you know. So you can have situations. So when the coefficient is negative, it has a negative, it reduces the overall value. So the positive coefficients suggests, actually suggests that increases in both education, in both experience and education and experience lead to lead to lead to increases in salary. So if you have a negative coefficient like that 2.66 for blah blah blah, if you have some negative values, it means that as that thing increases, for instance, if you had a third predictor, which is say um um friendliness, if there's anything like friendliness that can be measured, I now have minus 3.4. So it means that for every additional level of friendliness, the person loses 3 points, like the person loses $3,400, something like that. So, so both education and experience lead to increases in salary, but experience, because of the value, right? Experience has a much, a much stronger impact. Okay. So that brings us to the end of this. If you have not subscribed to this channel, be sure to do that. Don't forget to hit the notification bell also so you can always get alerted when a new video is released. And comment if you want me to teach a topic, let me know. If you want me to solve a problem, let me know. And of course, I can always find time to do that. And then don't forget to like and share so that more people can have access to all this great learning. So watch out for the next video, which where I'll be showing you the Python code for multiple regression analysis. So that makes things way easier. But here I've given you the background. So whatever you're seeing there, this is the background to it, like the idea of all those matrices you're seeing, the inverses and everything. The only thing is that coding makes it way easier to handle. You want to know how to go about the code, everything goes better. So till then, see you. Have a nice time.